Good morning and welcome to track 6. This track is about software engineering and productivity. We've had this track from the beginning of this program, and this was the very first training program that we knew about that had this particular track included as a part of extreme scale computing training. And that is because the awareness that knowing about how to maintain your software and how to do it right and how to increase worker productivity it was, has taken a long time to be recognized as an important area of endeavor. In the beginning also, it was true that when we would get the, and things have changed a lot. So the very first year when we started this track and we asked people how many had used a version control system, there were very few hands that went up. 2 years ago, when we asked the same question, almost everybody in the room raised their hands, and we found, much to our chagrin, that the content was too low level for most of the students, because by that time, most of the people had become aware that things like version control and software engineering was actually a useful thing to do, and GitHub played a role in that. So then at least we could reduce the introductory level content that we had in this program, and it was refashioned. So in today's track, you will hear about best practices, the things that have been successful in many projects, and things that are generally found to be useful. I want to say upfront that our intention is not to tell you what to do, or force any sort of system down your throats. Our intention is to make you aware of practices that have been successful, that people who have been using them have found useful, and this is all done by the Ideas project. So the content has been put together by the Ideas project. Ideas project is a project that was started by the Department of Energy to address the problem of software productivity, and the people who came together into the project are people who have been in the business of producing large-scale computing software, whether it is in the form of numerical libraries or in form of application codes, but they've been doing it for more than a decade, and so the collection of people is actually a group of people that sort of taught themselves how software engineering was helpful to them, because it is still true that the software engineering community that's out there and the kind of research it does is much more oriented towards production level software. So, and as an anecdote, I was recently at a software at a software conference. ICSE, it is the biggest conference in software engineering. And the thing that I noticed was that all of the papers presented discussion about software engineering practices as they applied to enterprise software when it was ready for release, when it was ready to be deployed. I asked questions from at least in 3 different sessions about what happened in the research departments, where the software was being used for the purpose of exploration, and the interesting answer was they were all flummoxed. They didn't know what kind of software engineering, if at all, was used in their own research departments. So the point that I'm trying to make here is that when a software is designed for the purpose of exploration, there is very little that is known about or researched about in terms of the software engineering practices that work. So the best we can do is the accumulated experience from various practitioners in the field, which is what the Ideas project is doing, is collecting this information and disseminating. Also, so we have generated a site called Better Scientific Software. The stickers for that are out there if you want, and this is a portal that is for purpose of collecting information, collecting resources about scientific productivity, software productivity, and we are always looking for people to contribute to this and also engage with the with the portal. Okay, this doesn't work. So this is the usual license in acknowledgement. And to reiterate, the theme of today's lectures is that good scientific process requires good software practices, and that good software practices will increase scientific productivity. And the reason, and in particular, for the kind of systems that you all are here to learn about, that is extreme scale computing, where you're working with leadership class machines, it's not an exaggeration to say that they are installations like the largest ones for scientific purposes in the world, such as the LHC here. So that's LHC, the Large Hadron Collider, and this is Theta, the current machine on floors for the machine that is in production at Argonne for leadership class computing. They are extremely expensive pieces of equipment, and therefore it behooves us to use them well, use these resources well to justify getting them installed and so on. And that in order to use, so everybody understands the need for this. The need for having good software productivity practices and good software, also the scientific practices that bear scrutiny is not as well understood for Theta. So what we want to do is we want you, the future scientists, future users of these machines and current users of these machines, to be aware of how to go about using these machines well. What these things do, the practices that we are going to be talking about today to you are, they mitigate risk of not being able to get your results in time in the allocations that you have, and not having robust results. But these practices mitigate the risks, and it is never zero. And I want to start with a particular example of an instance where there was a software in production. The software had a very good, in fact, a state-of-the-art productivity process in place at the time that this incident happened. But the circumstances were so that all of those practices could not be completely deployed. So the situation was that, so this is about the Flash code. Flash is a multiphysics code that was designed for astrophysics. It is a code where there is a bunch of components available, and you put together components. You can pick, permute, and combine various components to generate different applications. So in 2005, a machine was made available to us. This was the first of the Blue Gene line, Blue Gene L, the light, and we were given about a month lead time to prepare for a simulation that would run for a week or 2 weeks at most. And so this was the largest machine that was available at that time. And then the machine was going to go behind the fence. So it's not, if we failed to run the simulations to completion in the time that was given to us, we wouldn't have any chance of repairing any mistakes that were made, et cetera, et cetera. So, and also the machine wasn't ready, wasn't given to us on a regular basis to use until the production time. It was like once a week we would be given a certain amount of time to do the testing. So we prepared the simulation, and there was a particular capability that needed to be added, which was tracer particles in the code that hadn't been existed, but the simulation that was planned needed that tracer particle capability. So in those 1.5 weeks of time, we had to produce this. And second of all, when we initially ran the tests, we found that no form of parallel I/O scaled on the machine. So there were two things that had to be prepared in this short period of time with very limited access to the machine being tested. And the I/O was, every processor just dumped its own data because no parallel I/O was working. So we ran into all sorts of issues when running this. So this was a quick and dirty development. The two things happened. in I/O, what happened was we realized that if you ran an ls in the directory where you were doing the computation, 15 minutes later you were talking to the systems administrators to kill your job, because of the number, the inodes in the file system were just so huge that there was no way even a simple ls could return. So then, on the fly, we had to generate a system of we had to generate a system of directories and subdirectories, etc., where the files would go, and we had to keep sweeping them out after every time snapshot was done. So this was happening in flight. But the other thing that we realized after the fact was that the particle tags, the thing that uniquely identifies each particle, had we were using a floating point, and they got rounded off, and so we got duplicated tags. Now, we had all the information available, but the outcome of that was we had to actually develop post-processing in order to get this data, in order to analyze the data. We had to figure, based upon the proximity of points in the particles, we had to separate out the particles that had the same tags. And so the simulation was done in 1.5 weeks. It took 6 months to develop the tools that would then let us get the data to have the confidence that what we were getting, the results we were getting were right. And so it was 6 months before the first round of results could even be obtained. So the cautionary tale here is that there was a software process in place. The code was tested regularly, but because the one instance where the full process was short-circuited, we had these troubles that come up. And that just highlights the importance of having a software process in place. So as I said before, the objective is to bring the knowledge of useful software engineering practices, not as anything that is must use. In fact, there are lectures later in the day today which will talk about how do you go about customizing the rigor of the software process that you are applying to your project, depending upon the size, the need, the reach, et cetera, of the project. Basically, this is one thing that people do not realize, and happens to them over and over again, is that people say, oh, I'm writing this code just to do attest this particular concept. So that's how the code gets written. When someone else comes along and says, oh, you have this code, it does these things, great, I can just make this change to it and it is going to serve my purpose. And before you know, accretion has been happening, your code has been growing, and if you don't give a thought to how it is going to grow, you have a disaster on your hands. So your code will live longer than you expect, unless you're prepared to remove all the files that you ever wrote just as soon as you're done with the objective of that exercise. It is going to be used by other people in ways you do not expect it to be, and so you must prepare for that. So in today's session, these are, I mean, you might have seen them on the agenda already, but the topics that we are going to cover are workflow, as in how can you define and use tools that are available out there to define the workflow, and the basic definitions that we're going to be using with some examples. Then that will be taught by Jared. Then agile methodologies to be used in small and large projects by David Bernhold. A very important topic of licensing by David Bernhold. And then a topic that has recently again gained a great deal of visibility in the community is reproducibility. And by reproducibility, we do not just mean exact reproducibility of the solution. It applies in a wider sense, in that believable science, the science where you can back whatever answers you're getting in ways that is a scientifically valid process. Verification and testing regime, testing, code coverage, and CI. And finally, we will talk about refactoring, not in the sense that the software engineering world does, but in the sense that us in scientific computing have to deal with it in terms of changing code with the change in platform architectures. So there are a few terms that I'm going to introduce, and one of them is the heroic programming. And this definition comes from Wikipedia. So I'll give you a few minutes, a few seconds to read this. the irony is that many scientific teams resemble heroic programming, and the bigger problem is that many of them do not even see anything wrong with the approach. So what is wrong with heroic programming? And my assertion is that in vast majority of scientific fields, the results that could have been obtained with a professor and a postdoc and a graduate student working together and writing a small piece of code and gaining insights have all mostly been mapped out. Now, understanding is greater, tools are bigger, and most of the time the codes that the applications that you're working with require higher fidelity in modeling. Higher fidelity in modeling means that we are likely to have many more heterogeneous solvers that are part of the same code. So what you get is more complex software. And when you have more complex software, there are many aspects to it that people need to deal with. There is the mathematical model that is understood by the domain scientist. There is the numerical methods that's understood by the applied mathematician. Then you have to do things like verification that comes under, that requires cooperation by everybody involved. And then, because we are talking about HPC platforms here and the leadership class platforms, all of these are required to run well on the systems that they're running on, so that you need performance engineers. So what happens is that these are now different roles and different responsibilities, and it's not possible for a single person to take on all these roles in large projects. Additionally, in extreme scale science, it's not just the code complexity, it is also planning of a simulation and analysis of the results is equally complex, and so there is a complex overall workflow involved. In all of these, there are very many moving parts that need to interoperate. For example, the simulation that I used as the first example, it's among the simplest that runs with the Flash code, and that already requires things like a discretized mesh, compressible hydrodynamics, Lagrangian tracer particles, and the infrastructure such as I/O for both the state variables as well as particles. And that's just the simplest one. Typically, a simulation that is using for Flash takes something like 5 to 6 different physics capabilities, because there's things like, it was designed for thermonuclear runaways like nova, supernova, etc. So you have this compressible hydrodynamics, you have a specialized equation of state, you have nuclear burning, you have let's see, a burning flame, etc., etc. So all of these things, and they have the data structures, the state variables are about the only thing in the mesh that have a similar structure in all of the variables, but all of the other solvers that I'm talking about, their data structures need to be different, their data moves differently relative to the mesh. And so you have to take into account different levels of parallelism and different parallel algorithms that are used to manage these different aspects of the code. So, and then because there is a variety of expertise needed, the only tractable way of developing such codes is separation of concerns. By separation of concerns, I mean that those who understand numerics shouldn't have to deal with the parallel aspects of the code very much. They need to understand it, but they shouldn't have to program to it. Similarly, those who understand performance engineering shouldn't have to have deep understanding of numerics. And the way you do it is by designing a framework in ways that you have proper encapsulation of capabilities. And this is, I'll talk a little bit more about it later. And so without a good well-defined process and workflow, these things do not happen well. And then with the onset of higher platform heterogeneity, these requirements are also not known a priori. They're unfolding. Till today, we don't know exactly what the next the machine that we are planning for, that's A21 and Frontier, the coming platforms, we don't know what they're going to be like. Nobody knows exactly what they're going to be like. And so we have to prepare for that. And because the life cycle of a code is a lot longer than the life cycle of these machines, it is completely counterproductive to design these codes and target these codes to a specific platform. So the codes have to be designed in ways that they outlive the platforms, and that it doesn't require writing from scratch for every new platform that comes along. Because if you did that, you'd never get any science done. By the time you finish writing the code for a platform, the platform will be obsolete. So, yes?
I don't understand how you're separating performance from numerics. So I thought, you'll get the performance of the numerics, so maybe it's a definition kind of.
So one of the talks later is going to address that much more explicitly, but I will say this, that numerics is where you can prototype your algorithm, say, in MATLAB. And that's where, or Python or whatever. And then the way you implement it on the HPC platform is a completely different thing. So, and that has traditionally been the place where we addressed the single core or single PE in the distributed memory machine models is where the implementation of the numerics was where this was addressed. And that continues to be the case, but now what that is going to do is have abstraction lifting, whereby you can write your numerical algorithms in much higher level semantics, syntax, and that there are code transformation tools that can do the targeted optimization for you. So that's what most of the people are looking into and going toward. Okay. All right, so, right, that point I've already made. The supercomputers change fast. So then I want to introduce you to another term, which is technical debt. Technical debt is that you do quick and dirty, and therefore you've acquired a debt, and then as more and more code accretes without cleaning up the code, you acquire interest on it, which means that later on when you want to make changes to the code, when you want to do any alterations, then you have to put in more work because of the technical debt. So, and the way you acquire technical debt is that your accretion is leading to unmanageable software, increasing cost of maintenance, and it may even make the software unavailable, unusable at times. And so it is what is a consequence of choices. And that is that quick and dirty collects interest, which means more effort required to add features. That's my phone. And it's far away from me, so I can't turn it off. So it seems I'll give you a few more seconds to read this while I grab my phone and turn its ringer off. Oh, okay, thank you. So now switching gears, some of the challenges that are there in developing scientific application, there is technical, and the technicals are that actually we don't have a converged idea of what that code ought to be. All parts of the code are undergoing research in some sense, because we are always exploring new regimes, and so whether it is the domain science, it's the numerics, it's the architecture, it is the programming models, everything is going research. And also the requirements change throughout as the knowledge goes. The verification process is complicated by floating point arithmetic, because you bitwise reproduction in parallel environment, as soon as you have a reduction, you cannot do it. And there are many other. And then when you go into the threading model, then you have a non-deterministic order in which things complete, and so you cannot have bitwise reproduction. And that, and sometimes, and this is the problem, when you're working with a multi-scale problem, it can be very challenging to differentiate between a numerical drift that has happened, because there are very many different scales. So a very small scale phenomena may be introducing small perturbations in the solution, and you don't know whether they are because there's something wrong with that solution, or they're happening because of machine precision issues, which the floating point round off will bring in. And so this is an art. The ability to differentiate between them is an absolute art that needs to be understood. And then there are the sociological, and because you can design a software really well and you want it encapsulated, modular and all that, and you follow the object-oriented principles, but then real world is messy. If it wants to have a lateral interaction, it has to have a lateral interaction. There's no getting around it. And so sometimes software gets messy because the real world is messy. And in addition to that, there are the sociological challenges, because as you all know, since you are in the scientific world, is that in science domains, people are judged based upon their publication output, not upon the quality of software they're producing. And so there's a tension between the two. Most teams, funding agencies still haven't gotten around to this idea that in a scientific project, you need to have software engineers and developers as well, so they don't provide any funding for it. It's hard to get funding for it, so you are working with limited resources. And most people, until they are actually bitten by this themselves and have had an experience of something blowing up in their face by not having a software process, view it as an overhead. And so they just see it as an overhead that doesn't return any benefit. And the biggest one in these kinds of projects where you need to have people from various disciplines coming together is the interdisciplinary interactions, because there is the terminology differs among different domains and people are suspicious of each other. They do not understand the complexity of the work that the other team is doing, and so they're suspicious in terms of why do they need that many resources and why aren't they able to deliver a result much faster than this, et cetera, et cetera. All these things come into play. So for science applications, one needs certain customizations of the standard software engineering practices, because the extent and granularity of methods that are applied in scientific domain is reflective of the project priorities, because a small team need not have too much formality, whereas a larger team will need more formality in order to be productive. And then there has to be a sort of meeting point between the life cycle of science compared to the life cycle of software development, because and that is reflected. So the development model historically in most of the communities has been ad hoc, though it resembles, if anything, agile model more than any other, because that model is much more responsive to the needs of life cycle. And I want to point out this as a schematic for the way a typical scientific software development would happen and the needs that it has. So there's a physical world which is modeled using equations of some sort. They can be partial differential equations or any other kind of equations. And then those equations are discretized, and then numerical solvers are implemented for it. Now, sometimes when you are looking at these numerical methods, what may end up happening is you realize that the particular method you picked is not adequate for model fidelity. For example, in one of the projects that I was involved with, there was a modeling of radiation going on, and the ILU method was implemented. The method was beautifully converging, it was scaling really well, et cetera, except that it wasn't producing scientifically acceptable results. It was inadequate to model, to capture the phenomena. So then, because it did not meet the model fidelity, the whole situation here was changed and a different method was introduced. Similarly, then you have the numerical solver is implemented, and then you have to verify its accuracy and stability, and sometimes that may lead to a feedback loop if you find that there isn't enough accuracy that is obtained from that particular numerical method. And then validation is typically, we think of validation as confronting the results of simulation against some form of observation. It could be an astronomical observation, like the real from with a telescope, or it could be something that came from an experiment. And in all of these, even in validation, whenever model fidelity is better understood, the equations change and so on. So all of this cycle has all these feedback loops, and that's because everything here is, the knowledge base is growing, and that keeps on tweaking the that keeps on tweaking all of these stages as better understanding happens. So this is what we view as a software productivity life cycle. This is courtesy of Ideas Project again, where you have the model and software development, you have testing and verification, simulation, analysis and validation, and experimental design, which basically is driven by the science question, and if done right, ultimately results in scientific discovery. And within that, there is this process, you have analysis, software development, execution, workflow, and productivity. So what do we consider best practices in this field, software process best practice? One thing that is absolutely important is to invest in extensible software design, because like I said in one of the earlier slides, don't assume that your code is not going to grow. It is going to grow, unless you've written an absolutely useless code, crappy code. It is going to grow, right? So, and once you plan for that, then use version control and definitely automated testing. So version control, I think that all of you understand. Is there anyone in this room who doesn't get behind the idea that version control is an absolutely useful thing to do? You can raise your hand if you want to argue with that. Right. So version control. Now automated testing. How many of you do automated testing in your work? Okay. Not enough people. To those of you who do automated testing, would you work without automated testing ever again? You would? Okay, I want to hear why.
So because sometimes they are, they are not strictly necessary for my short-term needs, and I very often happen to miss short-term deadlines because I tend to write better my code. So, for example, I have weekly teleconferences in which I am expected to show updates on what I'm doing, and these are not the things that.
But that's not automated testing.
Yeah, but the time I spend in writing those things, I don't know. I spend one afternoon a week, and one afternoon a week it's a considerable amount of time.
Okay, so here is a clear.
Probably because the codes I use are not. It's not. My half afternoon will not be exploded by other 10 people. So if we were a team of many people, I understand that the half a day would be. Yeah,
but the whole idea of automated testing is that it should run nightly or on a regular cadence without you having to intervene. It should just happen.
I have to code them.
It's the write the code, it's the test. Something has to spend time and effort on writing.
Okay, so this is great. This is a great discussion, because if you want to argue that you shouldn't have to spend time writing a test, how do you have any confidence in your software? So when you're developing your software, you're writing a test for it. So why shouldn't that test just become a part of your automated test suite?
Yeah, you can, but later on somebody else could change the code, or you change the code. You also have to change that part of the code. Sometimes.
So a new test comes along, and that should become a part of the test suite.
So things can become complicated when you put a part of the code as a testing code, and then you have to test your code, write another code properly to test your test code, and it becomes more complicated.
I want to ask how automated you would make these tests. Like if I have a code that just outputs some binary blob of data. And normally what I was doing was running it, looking at the output binary blob, and I just know from the math what it's supposed to look like. I mean, I could automate the process of running and generating all these binary blobs and manually looking through them myself. But if I want to write something that somehow actually analyzes this binary blob, I mean, that gets a little more complicated.
So, okay, this is something that will be addressed later on, but I will give you the simplest answer is to have a binary blob as a benchmark, and just run a comparison, right? That doesn't take anything to do. So once you have established a gold standard for what the output ought to be, then you just need to compare that against what you're running, and that is automatable. Well, in any case, yes?
About the discussion always against the testing. I reserve 1/3 of my life for testing, and I'm soon going to testing and shopping.
Right, there you go. Because a code is only as good as the testing that, I mean, if a code is not well tested, you can have no confidence in its ability to deliver science. You shouldn't. You shouldn't be counting on that science as valid science if you aren't testing it enough. And we will come back to this discussion later on in the, yes?
So one more comment. I think automated testing for our performance tools is very difficult, in part because it's all using asynchronous sampling. But the biggest problem is that it's supposed to run on these leadership computing facilities, and there is no infrastructure for automated testing where things get launched through the batch queues and whatnot on these various systems. So that's the biggest impediment for us. And I know that there's an effort in the exascale computing project to try and remedy that with GitLab. But I can tell you that without that, the testing problem is harder than writing the software itself.
Right. So that's an impediment to running it, but if you had the ability, wouldn't you much rather?
Sure.
There you go. That was the point. Right. Yes, agreed. Okay. But even so, so this goes back to the point, institute a rigorous verification and validation regime, because without that, how can you have any confidence in the results? Define coding and testing standards. These are very useful for being able to maintaining the code later on, because what happens is if you have good naming standards, then just by looking at a file or a function, you can tell which part of the code it comes from. Otherwise, it can be extremely difficult to trace that. It is also very useful to have clear and well-defined policies for auditing and maintenance, distribution and contribution, and documentation. And you will hear about all of these in more details as the day progresses. Some of the desirable, which are not necessarily, which are harder to do, but add to good scientific practices, are provenance and reproducibility, life cycle management, open development, and frequent releases. Open development and frequent releases is mostly because it motivates people to not write sloppy code. When the code, when it's under scrutiny continuously, that's what happens. In the area of Flash code where I come from, we have all of these practices of auditing, maintenance, et cetera, but let me tell you, the only time that the test suite has a green light everywhere is just before a release. The only time our documentation comes up to the required standards is at the time of release. And the only time that people make sure that things like user's guide are updated and that the coding standard violations are all eliminated and the code looks professional is at the time of release. So that's why those things are important. And with that, there are some useful resources to get more of information. So there's the what is docs and how to docs. What is docs defines some of these practices, such as what is testing, what is portable performance, et cetera, and then how to are these very short descriptions of how you can go about doing these things. So these are usually 1 to 2 page sort of easily readable documents that you can access, very brief sketches. And other useful resources are the Software Institute in UK, Software Carpentry, the Community Codes Workshop, and all of these various journals that you'll have access to. Now, in the last minute or so, I want to talk in particular about community codes and why community codes are useful in scientific world. It is because when there are community codes in a community, a person that's coming in new doesn't have to start writing their codes from scratch. What they can do is they can look at the codes that are available out there, find out, see which one of them is closest to their needs, pick that code up, and if that code has extensibility and customizability built into it, then they can just add the things they need into it and customize it in way they do. And so they get productive much more rapidly than the communities that do not have such community codes. So, but it is also important to realize that just having a community code does not preclude the need for users to understand what they're doing with it, which means that they should have been able to write their code. It's just that they're not writing, because at least they should be able to scrutinize their results coming out of the code and being able to use the codes well, otherwise their results will be questionable again. And so what it brings about also is code component is reused. There is no need to become an expert in every numerical technique. If you know how to test a numerical technique for your purposes, that's good enough. Because the codes are more stress tested in communities, you know that your results are more likely to be good. And open source science results in more, it's generally good for the credibility. And so I'll skip over this one because I'm out of town. Communities that are there are many communities that are using community codes. But the last takeaway points that I wanted to mention are that good software practices are needed for scientific productivity. Software process does need to address reality in the sense that what are the resources of the team and how much overhead it can take. It is extremely important to recognize, that's the last thought I want you to go with, is that it's extremely important to recognize that science through computing is only as good as the software that produces it.